There we go. So welcome everybody to lecture A.6. As I said earlier, today we'll discuss limitations of interactive proofs. And specifically, we're going to try to study what happens to the power of interactive proofs as we try to kind of make, let's say, less and less randomness as less and less communication. For example, you could try to ask in the extreme, what is the power of interactive proofs where the prover sends one bit to the verifier? So I have here this parameter PC, stands for prover communication. And here I'm writing PC equals 1, which means that I'm going to consider the set of languages decidable via interactive proofs where the prover sends one bit only to the verifier, right? So that's not a lot of information coming from the prover. And one might think, is this class trivial? Is it like too limited? Well, probably it's not trivial. For example, we have seen an interactive proof that falls in this category, and that was the interactive proof for graph non-isomorphism, right? In that case, the proof that we saw, the prover was trying to tell the verifier which of the two graphs it thinks the scrambled graph received from the verifier is isomorphic to, right? And so just telling whether it was isomorphic to G0 or G1, that was like this only thing the prover did during that protocol. And because G and I is not known to be in P, this means that even in the extremal case where the prover just says one bit of information, says one bit, possibly there is something that non-trivial can be done. But more generally, G and I is also a very specific language. We've seen interactive proofs for many more languages. So we'd like to try to understand what can be done. So for example, like a very, very natural question is, let's take the case of SAT, okay? That's a canonical NP-complete language. Could we have an interactive proof where the total number of bits sent from the prover to the verifier, let's say, is a sublinear, little o of n, okay? Sublinear in n. Sublinear in the number of variables, right? Now, we do have an interactive proof where the prover sends to the verifier just the full assignment, right? With n bits. That's the trivial interactive proof. And in some sense, the question of could we expect SAT to have an interactive proof with sublinear communication is asking, is there something the interactive proofs bring in terms of communication efficiency over the trivial interactive proof, let's say for NP-complete languages like SAT? Okay, it's like a very natural question. And if you see, so far, the interactive proofs that we've seen don't really answer this question, right? We've seen how, for example, the sum check protocol can help us with an interactive proof for the unsatisfiability of a the unsatisfiability of a formula, right? So instead of checking whether all assignments do not satisfy the formula, we can just run the sum check protocol on its arithmetization. We also saw how an even more precise arithmetization lets you count the number of satisfying assignments. But in all of those cases, the prover was still sending at least n bits to the verifier. So what if the question that we had was purely, is there a satisfying assignment or not, right? And subsequently, when we worked with P-space, TQBF, again, the communication complexity was at least n. And even beyond that, in the last lecture, when we talked about doubly efficient interactive proofs, those questions were not even about satisfiability. They were about whether a circuit outputs a particular output or not. So those were circuit evaluation questions rather than circuit satisfaction questions. They were about tractable questions, okay? So you don't really have a good understanding about whether something like this is possible or not. So to formally study this question, we're gonna consider parametrized complexity classes, interactive proofs, where the prover sends PC bits of communication, the verifier sends VC bits in back, right? So these are the sum of all the sizes of the verifier messages. And the verifier uses VR bits of randomness, okay? So verifier randomness, okay? And similarly, we can consider AM to be the same thing, but we restrict the interactive proof to be public coin, okay? Oopsie. And so the goal of this lecture is to try to understand, as a function of these parameters, how hard the language can be. Okay, in order so that we can we will hopefully be able to answer questions of this sort. All right. So, are there any questions so far?
Are these parameters for every round or for the total, for the entire protocol?
Good question. These are parameters for the total. Okay. So, if you have maybe 10 rounds, you're might be sending PC over 10 in each one of those. Okay, and then total PC over 10 plus PC over 10 plus PC over 10 times, that's PC. Okay, so it's total. There's a question about AM. AM is a historical kind of a name. It stands for Arthur Merlin. We've briefly seen this class once before. It doesn't really matter why Arthur and Merlin right now. That's usually what is used to denote public key interactive proofs. So there's a question about, what about soundness? We're going to be fixing soundness to be, let's say, 2/3 and 1/3. 2/3 completeness, 1/3 soundness. Everything that we say today can be parameterized against completeness adders and soundness adders. That's actually a good exercise. But we'll assume, yeah.
If we consider soundness to be like less than 2/3, you say, then this interactive proof with only 1 bit of communication from the prover, like soundness is not enough, right?
Yeah, so I guess think about O of 1 here, right?
Okay, perfect.
And again, everything that we say today can be parameterized against general sound completeness adder and soundness adders, and they will. Anything that we see, you have more refined expressions where those parameterized adders appear. Okay, so you can imagine having 5 parameters instead of 3, 2 more for completeness adder and soundness adder, and they will be like a refined theorems. Okay, perfect. But what we see today will be kind of those theorems with some constant soundness. Okay, and here, like the 1 bit is my focus was not so much on the 1 bit versus 5 bits. It was like some constant number of bits as opposed to something else. Okay.
Right, thanks.
Any further questions?
Hi, can you hear me?
Yeah.
Yeah, so I had a question about, you mentioned something about circuit evaluation and circuit satisfaction. So I wasn't clear, like, did we switch models in between while trying to construct interactive proofs? My impression was that we are taking the same problem of checking whether X belongs to L and trying to create IPs for it.
No, we haven't changed any models. We're always considering X is in L, X is not in L, right? But the language itself may be a deterministic or a non-deterministic language, right? So SAT is a so-called non-deterministic language because it's decidable via a non-deterministic machine, right? But when we studied doubly efficient interactive proofs, we did not ask a question about satisfiability. It was a question about evaluation, okay? Does a circuit on input X, the input X that I'm giving you, output 0 or 1 or whatever. I'm not asking, does there exist an input X such that, blah, 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 right? So the chained sum check protocol that we saw last time for doubly efficient interactive proofs was absolutely not about satisfiability questions. It was saying that the verifier knows the input, it is just lazy, doesn't want to evaluate the circuit over it, so it delegates the computation to the prover, okay? SAT is not something that the verifier could, even a non-lazy verifier would be able to solve on its own, right? That is a NP complete problem, and at minimum, it needs the prover to send a candidate assignment, and we're asking, is there anything better than that? Okay, then sending a candidate on my assignment.
What about the co-set problem that we saw? Unset, sorry. Was that circuit satisfaction, circuit evaluation?
It's neither. It's I mean, it's a for all question, right? So technically it's a co-problem to a non-deterministic problem, right? Because non-deterministic says there exists something such that, right? And co-problems about non-deterministic problems are problems of the sort, for all objects of some sort, something happens. Okay, so it's like a complement of that.
But then can't we think of it as an sum of the evaluations at different points? That's what the prover was proving, right? In unsat, that the circuit evaluates, the sum of evaluations of the circuit is 0 at all points.
I think we're getting into semantics and precisely, NP and co-NP, those are two different classes. SAT is NP complete and co-NP is and unsat is co-NP complete, and sharp SAT is kind of sharp P complete, and that's just what it is. This idea of non-deterministic, deterministic, these are like helpful terminology, but at the end of the day, sort of kind of they can all be defined in precise ways, and they're different objects. So. But with time, I think sort of the intuition of how they're different, I think, sort of becomes clear again. So if you have like an exponential sum, that's not really like an evaluation question. It's an exponential sum. So, and then finally, there's a question by Tal about why is this interesting? Well, yeah, because it is NP complete, and generally speaking, NP complete problems are very expressive. And so we're interested to kind of have non-trivial interactive proofs about them. Any further questions at this point? There's a question about what about if the reduction blows up more than linear? Yeah, sure. So we can ask the question about square root n or cube root n. Anyways, we're like these are things we need to be comfortable with in terms of like in the best case scenario, we would have an interactive proof for SAT with 5 bits, right? Here we're asking, is there even something that is minimally non-trivial, right? Never mind taking a reduction and then doing that for something else, right? Okay, so what we're going to see is primarily bad news about interactive proofs. They're not really cut out for handling certain types of languages. The first theorem we're going to prove is to basically like a refined version of the upper bound on interactive proofs that we've seen in the first lecture. In the first lecture, we were primarily interested in upper bounding interactive proofs in terms of space. We saw that every language decidable via an interactive proof is decidable in polynomial space. Here we'll see that every language decidable with these bounds on the resources can be decided in deterministic time. There's exponential in those bounds. Okay, this is not entirely surprising, but it will help us sort of set the stage for more complex theorems. And specifically the next one, we're going to say that even if I put no bound on the verifier randomness, morally we get the same upper bound. The main difference is that my algorithm that runs in exponential time, now it will additionally need the use of randomness itself. Okay, so if you have an interactive proof with like very small communication, regardless of how much randomness the verifier uses, there is some kind of probabilistic algorithm that will decide the language in time that is exponential in the transcript alone, excluding the randomness. Okay, and this will be already like a little bit require one new idea to prove it. And even more interesting, in the case of public coin interactive proofs, where we are bounding only the prover communication, so the verifier could be sending a lot of information to the prover, still we have an upper bound that is exponential just in the prover communication alone. All right, so here we might ask, what about if we have private coin interactive proofs? Well, there's an answer to that as well. It's basically the same answer, but I need to give you an NP overhaul. Okay, so it's a probabilistic algorithm that is allowed to solve problems in NP for free. So now let's try to get these in context against the theorems we've proved already. Okay, sorry, before that, just wanted to say that all of this, the main takeaway is that there is a relation between the communication complexity of an interactive proof and the time complexity of the language it decides. So the less bits are sent from the prover to the verifier, at the end of the day, this makes the language easier and easier to decide. with or without an NP oracle as a function of whether you have a public coin or a private coin protocol. So, for example, let's see. GNI is a language that we've seen had a private coin protocol, right? There was this random bit B, okay, that it was not revealed to the prover, okay, and the prover was asked to guess it. So that means that GNI falls under theorem 4, right? Which is what we expect. Why? We would not have expected to have a theorem like this one for general interactive proofs, because if we did have that, it would have told me that GNI is in BP time 2 to the order of 1 times poly n. In other words, it would have told us that GNI is in BPP. Now, GNI may or may not be in BPP. It is not known. Currently, it is not known to be in BPP. Therefore, it is not surprising that GNI falls under theorem 4, where given an NP oracle, now it is something that actually doesn't surprise us that we would have been able to solve GNI in BPP to the NP, right? At the same time, there is a protocol that we did not see in this course. I'm just telling you, there is a way to turn the GNI protocol from a private coin protocol to a public coin protocol. Okay, this is the so-called Goldwasser-Zipser transformation that if you want to learn about it, you can see one of the lectures from my fall 2020 course is just one of those lectures that we had to cut out for this 2-week summer school. But the main point is that when you transform the private coin protocol about GNI into a public coin protocol, now the prover is actually sending a lot more information, which is great, because then we don't get a contradiction or just something strange happening here. It would tell us that we have a protocol for GNI where the prover sends n squared bits of information. It means that GNI is decidable in BPP in time 2 to the n squared, which is normal. Okay, that's what we would expect to happen. Okay, so in some sense, the difference between theorem 3 and theorem 4 is reflected by the fact that the transformation from private coin to public coin protocols does not preserve prover communication. Okay.
I have a question.
Yeah.
Why are these theorems bad news?
Okay, well, I'm getting there. So let me finish with this observation. Oh, there is that. Okay. So why is this theorem bad news? So let's take, for example, the case of 3SAT. Okay. Let's say that if we had, let's say that we somehow figured out that 3SAT is in AM, PC, say n to the 1/3. Okay. Maybe there is some way to use the sum check protocol to kind of arithmetize 3SAT and I don't know, have like, n to the 1/3 rounds, and in each round I'm sending like a small amount of information. Okay. Then through this theorem, what we would learn is that 3SAT is in BP time, basically, let's say 2 to the little of n. Okay. In fact, 2 to the n to the n1/3 times log n, right? Now, anybody can tell me what's the problem with this? Yeah, so this kind of runs counter to complexity conjectures such as the exponential time hypothesis, or more precisely in this case, the randomized exponential time hypothesis. Namely, it is believed that 3SAT cannot be decided by either a deterministic or even probabilistic machine in time that is 2 to the little of n. Okay, so this is, we don't know whether that's the case or not, but it is a widely accepted complexity conjecture. Okay, that's somehow 3SAT is kind of exponentially hard. It's not just in the worst case more than polynomial time, but we do not expect, let's say, some sub-exponential algorithm for deciding 3SAT. Okay. And there's a question by Tal, it could be that 3SAT is in the M PC n to n over log n, and yes, it is. For all we know, it's possible. And I just leave it at that. There are slightly stronger theorems about both 3 and 4 that I'm not stating here. So I'll kind of, it's not the tightest things you can imagine. So right now I'm sort of not trying to delineate exactly the boundary between what's believed and what might still be open. But intuitively, the point here is that through this theorem 3, okay, this basically rules out any non-trivial interactive proof for NP-complete languages as long as they're public coin. This one by itself doesn't say that if you use private coins you can't get it, but there's another theorem that I didn't state here. Maybe I'll add it later. That tells us that even with private coins you don't expect something non-trivial to happen for NP-complete languages. Okay, but for now let's just focus on this one because kind of anything interesting we've seen in this course, sum check, Chemise's protocol, double efficient interactive proofs, they're all of them, any non-trivial kind of technique we've learned about interactive proofs, they're all public coin, okay? And so this already tells us that kind of variations of sum check protocols, variations of Chemise's protocol, they're just not going to help us here, okay? There's a question about, why is theorem 1 and theorem 2 bad news? Well, because those are also limitations, right? They're maybe not as strong limitations as theorem 3. So you can think theorem 1 is, kind of bad. Theorem 2 is worse, and theorem 3 is worse, right? In particular 3, we can just write this strong conclusion. Theorem 2, you can say, well, you don't have a 3-set protocol where the even private coin, where the verifier and the prover send n to the 1/3 bits of communication, right? So, like as you go up, you have more and more constraints in order to derive a bad news. Okay, but either way, they're all telling you that if you have few resources, the language is easier and easier to decide. Okay, and so if your language was hard in some sense, for example, 3-sat is believed to exponentially hard, then that imposes limitations into what kind of things you can hope on the left-hand side. Okay. So one way you can think about this whole direction is basically designing fast algorithms for interactive proofs. Okay, that's roughly what this is about. You exploit the fact that you have an interactive proof for a language to design a fast algorithm for it, which means that if you didn't believe there's a fast algorithm for a language, then you shouldn't believe that there was an interactive proof with those parameters. Okay, so this is kind of like a rather direct way to investigate the limitations of interactive proofs. All right, so today, what we'll specifically do, we will focus on these two. And this one is basically a slightly harder version of this one. And then this one is, it's more complicated. There is a, you can look in the lecture notes for references. There's a very well done paper that proves all of these in one place. It's a paper by Oded Aldreich and Johan Hasted. Great. Any further questions before we start proving theorem 1, theorem 2? Take a note. I want to add some observation about 3-sat in this slide. Now, you will later today with Tom start constructing PCPs for NP-complete languages. Okay, so you've gone through like a few lectures on property testing, linearity testing, validity testing, and then 2 fun lectures on Fry. And one of the differences between interactive proofs and PCPs is that interactive proofs are not well suited for NP-complete problems, but as you will see today and tomorrow in constructions of PCPs, there are fairly natural arithmetization and validity testing approaches to obtain pretty good PCPs for NP-complete languages. Okay, some interactive proofs behave rather unusually for natural languages of interest. They primarily work better for things like either circuit evaluation or counting problems, okay? Kind of beyond NP. Further questions now? Because we're about to kind of switch gears and jump into theorem 1. Okay, so let's continue. So we have encountered the game tree of an interactive proof rather intuitively the last time that we talked about an upper bound for interactive proofs, when we said that IP is in P space. This time we're going to revisit it slightly more precisely, because somehow having a bit more explicit notation and terminology for the game tree will actually enable us to prove these more fine-grained theorems. So let's say that a transcript of interaction is a tuple of prover message, verifier message, prover message, verifier message, so on and so forth, up to the number of rounds. And then we're going to say that an augmented transcript is the same thing when I tag at the end the verifier randomness, okay? Which, potentially there's some there is randomness used by the verifier, and we just like attach it at the end. Okay, that's an augmented transcript. So now fix a verifier V and an instance X, and the game tree of the verifier V and instance X is a tree of all possible augmented transcripts. So the way you want to visualize it is that you have kind of one jump for each move, right? And at the very end, you have the consistent randomness here. So it would look like this. There is all the prover moves, then all the verifier moves, then all the prover moves, and so on and so forth in alternating fashion until the interaction is over. And then we just put on all the consistent augmentations. So all the random strings that are consistent with the transcript of interaction. Okay? So this means that prover moves at level 2i, right? At level 0, at level 2, at level 4, right? And the verifier moves at level 2i plus 1 at odd levels. It moves at level 1, at level 3, and so on and so forth, right? And edges from an even level to an odd level are possible moves by the prover. And edges from an odd level to an even level are possible moves by the verifier. And the edges in the last layer are possible random strings consistent with the transcript. Okay? Oopsie. So far, I should have just put in I don't know, like notation and terminology, things that should probably already be quite familiar to you. Any questions about the game tree? There's a question of, what about if the honest prover is randomized, for example, in ZKIP? That's still fine. The prover has some number of moves. These are all the ones of the prover. And, in that case, let me see. Maybe we have to encounter maybe we need to put in randomness as well, but let's just ignore that, okay? So it's a good question. I'm sure it's going to be like a simple exercise to extend whatever we're saying for ZK. Either way, we are here to prove lower bounds. And so whatever we want to prove for limitations of an interactive proof will only be harsher with zero knowledge. And indeed, will be discussed last time actually about zero knowledge. And once you introduce zero knowledge, actually, there's not a whole lot you can say, because there is a lot you can say, but the language is inside AM intersect co-AM. So there's like different types of upper bounds you would prove in that case. Is it always this prover that starts? Well, if it doesn't start, it can start by saying nothing, and then the verifier moves. These are like, somehow it doesn't matter. Like it's just some way to notationally pin down. We're not specifically bothered by whether there's an empty round, there's dummy move or not. We're not concerned about those edge cases. Just kind of normalize things in ways that you can write it down sanely. You could have also decided to do it the other way, and it would have been just fine. Okay. This is just so that we have some handles. Further questions? Great. So one realization is that, as I'll explain, it actually we don't really need to compute the value of the tree. It suffices to approximate it. So what is, anyways, the value of the tree? Well, the value of the tree is the value of the root over here. And it is recursively computed as follows, right? the value of a leaf node at a location down here is just the single bit that is the decision of the verifier given that transcript and the randomness down here, right? So at the bottom, the value is just either 0 or 1 as a function of whatever the verifier says, given that everything is known, right? The value of an internal node at an even level is the maximum of its children's values, right? Because the prover, when it moves, it will choose an action that maximizes the underlying values, right? It will want to increase its probability of winning. And the value of an internal node at an odd level is the weighted average of its children, right? Because the verifier will move randomly according to its randomness, right? But only among, of course, the randomness strings that are consistent with things so far, right? So there's going to be some weights on the probabilities of each verifier message, and you just take the weighted average of those, okay? And yeah, and this also includes the last layer where you're going to take, so according to those, whatever random strings are consistent with it, right? And if X is an L, then the value is at least, let's say, 2/3 or maybe equals to 1, because there exists a prover, the honest prover, that convinces the verifier with a probability at least 2/3, okay? So it means that, this way of assigning values will result into some values at least 2/3. Else, if X is not an L, then no prover can convince the verifier with more than 1/3 probability, so it means that the value of this tree is at most 1/3. Now, because there is always a required interactive proofs, some gap, okay? In this case, with this particular gap, to decide whether X is an L or X is not an L, it suffices to approximate the value of the tree to within, let's say, an additive factor of plus or minus 1/6, okay, which is half the distance between these two values, okay? In one case, kind of you're saying you want to be up here. The other case, you want to see one about here. There is a half in between. That's 1/6, right? So if you get the value right to within this range or that range, then you can distinguish the two cases, okay? So this is an important realization. To decide the language will suffice to approximate the value, not to compute it exactly, okay? Now, in the past, we have seen, actually in lecture 1, how to compute the value in polynomial space and exponential time, right? That was, how did we do it? We just basically showed that the optimal prover strategy, at the time we denoted it P star, is computable in polynomial space, okay? And in fact, also exponential time, because any algorithm running a certain amount of spaces runs in time at most exponentially in that. But today we want to try to be more careful about how to compute this value of the tree, okay? And specifically, not just as a function of the various parameters that we're bounding, the sizes of these things and the sizes of randomness, but also to just use the fact that we have the degree of freedom to approximate things instead, all right? Anyways, so this is just basically more precisely what we said last time. If you remember, P star was alternatively defined by an expectation or a probability and a maximum. So it was probability maximum, probability maximum, probability maximum, corresponding to whether the verifier moves randomly or the prover maximizes, right? And those are indeed these two kind of features of the game tree. Okay, and we just kind of laid it out slightly more precisely, or at least in a more tree explicit way. Any questions about this? This is just setting notation and setting kind of syntax. All right, I don't see questions, so.
I have a question. So in the proof for IP belongs to P space, we did a similar thing, but there we were dealing with completeness 1, right?
Yeah.
So is it also possible to extend this analysis to completeness 1, or here we are taking it 2 by 3, right?
Yeah. So the whole analysis we did didn't really care whether the completeness was 1 or not, because we were basically computing exactly the value of the tree. I think we had a name for it, which was Q sub x, okay? Which was the sum of all the possible decisions of the verifier with its 0 or 1 divided by the probability space, the number of verifier random choices, right? And we were just exactly computing the value of the tree, okay? That Qx, that was the value of the tree. So it doesn't really matter whether we're dealing with perfect completeness, imperfect completeness, whatever it was, that was the maximum convincing probability for that x, okay? And then, you go back to whether x is null or x is not null, and you sort of decide what needs to be done, right? As a function of what was the promise. As I said earlier, this 2/3 and 1/3, if you, in general, you could have them be, some alpha and some beta, and everything we say today, you can just try to pay attention to, the gap between alpha and beta. What matters is alpha minus beta, how big that is. And, it is a parameter that you could keep track of through an analysis. And in particular, when it's constant, it goes away. But if there are some functions of things, then, they will have some influence on the final time.
I have a question about what about the paths where the verifier aborts or rejects halfway? What are the remaining nodes then?
You can just, kind of pad them out with like dummy paths that end into a reject. Like it doesn't really matter. Okay. Like what matters in the end is like the values down here, right? So, if you have an abort, you can just continue it with like dummy messages, and at the end there's a 0. Somehow, rarely this type of misbehaviors are interesting. They're just primarily a question of just kind of encode them somehow in your sort of notation, and didn't really cause trouble. But yeah, good question. Further questions? Okay, so then let's continue. So now we're gonna go to prove the first theorem. Okay, the first theorem, just a reminder, is primarily a warm-up. We're going to say we're gonna have a parameter to upper bound the prover communication, the verifier communication, and the verifier randomness. And we'll say that any language decidable with these parameters, with an interactive proofs with these parameters, can also be decided by the deterministic algorithm that is exponential in those things, times some polynomial in the input. Okay, so let's give a name C to be the sum of all of these parameters. So it's basically a bound on the communication complexity and randomness. So this is actually like a pretty simple proof. Look, the number of nodes inside the game tree is at most 2 to the order of C, because look, there are at most 2 to the PC plus VC possible transcripts. So that's the number of internal nodes, right? Because overall, the prover sends PC bits, overall the verifier sends VC bits. So kind of the product of all the arities of prover messages and verifier messages combined is going to create at most 2 to the PC plus VC possible transcripts, okay? Because a transcript has PC plus VC bits. So whatever kind of blow up at each layer there are in the tree, total there's going to be at most 2 to the PC plus VC internal nodes, period. Now, these are transcripts. Then actually in the tree, we also have augmented transcripts. So kind of each augmented transcript has a further fan out of consistent random strings. Okay, well, we have a bound on a number of bits the verifier uses. There is at most 2 to the R possible augmentations for each of these transcripts. Okay, so overall, there's at most basically 2 times 2 to the PC plus VC plus VR leaves. Why the 2? Because when you add up things in a triangle, at most you get 2 times of that, right? Then there's a question that by Gregor, and I'll get back to that in a moment. But the point is that if we have at most this many leaves, we can compute the value exactly in 2 to the order of C poly n time by writing out the tree explicitly and just following the recursive computation. And in fact, exactly, we're not approximating. This is the same computation that we did, just I re-expressed it in terms of PC, VC, and VR. Okay, we already did this in lecture 1. This note addresses Gregor's question that, in fact, we can put a slightly more precise upper bound in the sense that it doesn't really matter what the verifier sends, just the fact that we have a bound on the verifier's randomness that just limits the fan out of verifier messages. So really, we can set C to be PC plus VR. Okay, so the number of augmented transcripts is at most 2 to the PC plus 2 to the PC times 2 to the VR. Oh, it's more like a small technical note. And maybe just kind of to really drill in, how do we compute the probabilities of verifier messages? Well, we can associate to each node where the verifier moves the set of all random strings consistent with the transcript so far. So like at the very beginning, we have it. And as we continue, we just keep trimming out, dropping the verifier randomness that is inconsistent with messages so far. And to generate the probability, we just iterate over this set, which will partition the set according to the verifier's move. So maybe for, I don't know, 10 choices of randomness of the verifier, it sends the same message, I don't know, hello, right? For other 15 choices of randomness, it sends, I don't know, good evening, right? And so these are going to create probabilities that we can associate to the verifier messages, all right? And we just keep track of them, starting from the beginning, which is all the randomnesses, all the way down, right? And at the very end, we're just automatically left with a randomness that is consistent with the augmented transcripts so far. And we can just write down all these things. Anyways, we have plenty of time, okay? And we currently don't even care about bounding the space, okay? We could even bound the space and slightly be more careful. Here, you can even imagine we're using exponential space as well. So you really write down the tree fully in memory and just do all this computation, okay? Now, of course, on the prover side, we're not partitioning randomness whenever the prover moves, that's just the prover's move, okay? So in particular, you should appreciate that the same randomness may appear in multiple leaves, okay? Because maybe the prover moved, okay? And the same randomness is consistent with partial transcripts so far for different prover moves. That's fine, okay? Okay, so we haven't really done anything. All we've done is to basically say, okay, well, there's a game tree. I can write it in memory, and it's not too large. And I can just conduct a computation and compute the value of the tree exactly, and then decide the language. So this is telling me that if all the prover messages and the verifier messages and verifier randomness are small, then the language cannot be too hard to decide, because if not, because I can just write out this tree and decide it. And if you get, for example, something here, say sub-exponential, and your problem you do not believe can be solved in sub-exponential time, then, well, you have a problem. You probably did not have an interactive proof with those parameters, okay? So this is like a very simple way to kind of appreciate, how bounds on the interactive proof resources translate into like fast algorithms for it, where fast just means, something exponential in those bounds, okay?
So I have a question. In the first note, you say that we can actually bound the verifier's communication by the verifier's randomness, but there can be like contrived IP protocols where the verifier messages isn't dependent on any randomness. Let's say it's a deterministic string, although it won't help the power of IP, but I don't see how you would also reduce the size of the transcript in that case.
I'm not saying that you can reduce the size of transcript. I'm just counting the number of transcripts. That's all. And the degrees of freedom on the verifier side are, kind of determined by its randomness. Okay. So whatever things they're sending, there is just they're of course of most polynomial size, at most polynomial. But beyond that, I'm mostly worried about the size of the tree, which is the number of degrees of freedom. And those are bounded by its verifier randomness. And yes, Amit, if there's anything that you can do to your microphone for next questions, it's a bit hard to hear you. I can mostly understand it, but maybe there's some way to fix it. Yeah, a great question. So I'm not sort of compressing the transcripts is more about the number of transcripts, okay? Further questions. This is like a very simple theorem, okay? It should just be like a time version, fine-grained version of upper bounds and interactive proof from lecture 1. Okay, so now we're going to go to theorem 2. And the main difference is that we are no longer going to assume that we have any bound on the verifier's randomness beyond some polynomial bound. Okay, of course, it's going to be something polynomial, but we don't know what it is. Okay, it's not something that we consider to be small. All right. Instead, we're going to only bound the amount of bits sent from the prover to the verifier and from the verifier to the prover. And we want to somehow argue that still, possibly by using randomness in the algorithm, you can still kind of decide the language fast, kind of exponential in the communication size alone. Now, so let's kind of redefine C to be a bound just on the communication. It is still the case there is at most 2 to the C possible transcripts and at most 2 to the order of C internal nodes, but now each transcript may have many augmentations, right? Because we don't know anymore that there is a small number of verified random bits. So we cannot construct T in the allotted time. So our allotted time is 2 to the order of C poly n, okay? And we just cannot write down the tree in full. We cannot afford it. When we get to the end, we may have just way too much randomness consistent with a particular transcript. All right? Is this point clear? All right. In fact, not only at the very end, but even the process of associating probabilities to verifier messages is something that we cannot afford, okay? Because the way we kind of associated probabilities to verifier messages was to start out with the whole set of possible randomnesses, and kind of as we go down, we see how many randomnesses are consistent with a particular verifier message, and also compute the probability as a function of that. So even that we cannot do, all right? So it's pretty annoying. Like it seems such a small change. We still have a small transcript, but somehow the fact that verifier randomness is a lot means that the exact probabilities of messages in order to compute the value of the tree are inaccessible to us. It would require us to iterate over all the verifier randomnesses. We cannot afford it. So here is going to be the first time that we're going to use the freedom to approximate the value of the tree rather than to compute it exactly. And we'll use it by taking advantage of the fact that now we're giving ourselves some slack. Rather than using a deterministic algorithm, we'll use a probabilistic algorithm, okay? So we'll use randomness to approximate the value of the tree and be correct with this approximation with some probability, okay? So here's the probabilistic algorithm. Actually, it's very simple. It's basically 2 steps, okay? So what we're going to do, the first step is going to be, you know what? We have too much verifier randomness. We're going to pick a random subset, okay, of representative random strings from the verifier. Okay, so I'm going to pick m of them, say with replacement. So I sample R1 from 0, 1 to the VR, I sample R2, R3, up to some Rm. Rm is a parameter now. And we'll eventually set this parameter to be exponential in C times C, so 2 to the C times C. And then we'll compute the value of a residual tree induced by this representative's choice of verifier randomness, okay? So we're going to compute the value of T of R, where T of R is the residual game tree obtained by omitting nodes inconsistent with R and adjusting the weights. So we're kind of like saying the verifier is playing the game, but it is not sampling randomness from within the whole set, but from some restricted set whose size we control, and it's roughly exponential in the transcript itself. Okay? So we're computing exactly the value of a related tree that is sampled from the original game tree. All right? There's a question of what is the H-like symbol? Sorry. This is meant to be a capital theta, meaning that it is no more than asymptotically to the C to the times C, but is at least that as well. Maybe I'll Maybe it's worth fixing that in my slides to make it more precise. Took a note of that. All right. Now, let's first look at the running time of this algorithm. Now, this algorithm will run in time 2 to the order of c poly n, because by definition, we have kind of sampled a representative set of randomness of size 2 to the c times c, right? C, of course, is poly n, right? And then we're computing exactly the size of a tree. I mean, the value of a tree whose randomness is bounded by the things we already have, okay? So great. So the algorithm does run in the allotted time. And we're just left to argue that the algorithm returns a value that is close to the original one with decent probability, okay? Like we have a candidate probabilistic algorithm that runs in the right time. We just don't know whether it's doing the right thing. So at very high level, the strategy is actually extremely natural. We have a tree that is too big because the verifier has too much randomness. We know we don't really need to compute the value exactly. So we just say, okay, we'll sample enough representative random strings for the verifier and compute the value exactly relative to a representative sample. And we want to argue that with decent probability, the exact value of the representative sample is close to the exact value of the full tree. All right? It's a pretty natural idea. Any questions about intuition for here? Right? Hopefully it is it's a pretty natural strategy, and yeah, we just need to analyze it. We have like a good candidate. So perhaps not surprisingly, things are going to come from concentration bounds. Okay, so we're going to use the concentration argument applied to, you know, as always, you need to figure out to what, right? The right random variables. Okay, so the statement we're going to prove is that with high probability over the choice of representative randomnesses for the verifier, the value of the residual game tree is not so far from the value of the original game tree. Okay, so this is saying that if we sample R at random, most of the time it is not too far, right? Remember, our target was to be, let's say, within 1/6, right? And this is saying that we'll be within 1/6 like 99% of the time. Okay, well, you know, 1% of the time we'll get something way out, but we don't care, right? Because we just need to decide with bounded error over the randomness of the algorithm. Okay. All right, there's a question by Alessandro. Does it imply that we do not need too much randomness for designing an IP? Or in other words, so randomness is a certain amount of randomness is always enough? Not quite, right? Because that would be saying that we have a transformation from an interactive proof with this amount of randomness to another interactive proof with, say, less randomness, okay? That is not what we're doing here. What we're transforming is going from an interactive proof with certain amount of randomness to a probabilistic algorithm, okay, that uses, say, less randomness. So it's a different object. The question you're asking is about de-randomizing interactive proofs, okay? And you know, that's like a different subject. One can talk about that, but you know, this is not, I'm not claiming that what we're doing here is that, okay? But it's a good question to study the randomization of interactive proofs. There are results about that out there, okay? Yeah, but then good question. So this is what we want to prove. Are we clear that if we prove this, we're done? Right? Okay, because if X is an L, we expect this to be at least 2/3. So if this one is pretty close to 2/3, then we know what to say. If X is not an L, then this one is at most 1/3. And so if we find this one to be, you know, pretty close to 1/3, like, you know, this much close, then we also know what to do. And we know it will be right, you know, very often. Okay, great. So if we need to apply concentration argument to the right random variables, let's define the random variables. So we're going to define V to the R to be the verifier that is restricted to sample randomness in R rather than the full space. Okay, so this is the honest verifier, except that the randomness it finds in its random tape, it is random, it's sampled at random from this R rather than from 0, 1 to the VR, okay, from the full space of randomnesses. So observe that the value of this residual game tree is nothing but the maximum acceptance probability of this residual verifier when interacting with any prover strategy, right? It's just that, right? Because if we restrict the verifier to this randomness, it is as if you let a prover, the optimal prover, some optimal prover, play against the residual verifier. That's just what it is. Now, for any prover strategy, P tilde, we can define certain quantities. Let's define delta of P tilde for the particular choice of randomness R, sorry, randomness set R, to be the difference in acceptance probabilities between the residual verifier, okay, and the full verifier, okay, which we can summarize this way, right? So we're going to write delta of P tilde and R is when, having fixed the set R and the malicious strategies of P tilde, we just compare how P tilde fares against the residual verifier and the full verifier. Okay, that's just what delta is, right? And I just wrote it out explicitly here. And here we have just some syntactic sugar. Okay. So notice that this quantity depends on R, and this one does not. Okay, because this is just the whatever P tilde does against the original verifier. Okay. So all we need to do is we need to argue that the difference delta is small with high probability over the choice of R. Okay? We'll see why that suffices in a moment. Okay? But we want to first argue that.
But the verifier is technically able to determine that he now gets actually samples from the restricted random tape.
The verifier doesn't think. The verifier just follows instructions. It sees randomness in the tape and it acts accordingly. So it doesn't think. So it is completely well-defined to talk about a verifier that receives randomness sampled according to some different distribution. The verifier always was going to be a deterministic algorithm on X and the given randomness, right?
But what if the verifier is just programmed if he determines that he's getting restricted randomness, then
it cannot determine it. This randomness is one of the valid choices from here.
Ah, okay.
It's just the distribution is different, and the verifier was going to do something on any given choice of random string, and we're just kind of changing the distribution slightly. Okay. And in some sense, what we're arguing is that it doesn't really matter as long as you take, and this set is large enough, then the behavior of this verifier cannot change too much from the original verifier because the transcript is not too large. Okay. You can think about it as some sort of like because the transcript is so small that many randomnesses kind of collide on similar behavior. So they didn't really need so much randomness to begin with. So is it possible that the prover that maximizes this one and this one are different? Yeah, it's completely possible, and we'll account for that later. And we have to use somewhere the fact that the transcript is small, and we'll use that for that. Good question, Amit. Great. So let's argue first that this difference is small with high probability over the choice of R for any choice of P tilde. Okay. So we're going to argue that for any choice of malicious verifier with high probability or with small probability over the choice of R, the P tilde cannot perform very differently between the two games. Okay. So fix any P tilde with high probability over R, then it basically wins with the same probability. Okay. Intuitively, this is because R is representative. Okay. So the proof is we're just going to basically rewrite this as some Chernoff bound and then apply a Chernoff bound. So we just need to We just need to define the variables. So let's define zi to be the single bit that determines whether p tilde convinces v on randomness Ri, where Ri is the ith random string in R. Okay? And the random variables Z1 through Zm are IID because R1 through Rm are. Remember that each of those is an independent sample from 0,1 to the VR, right? The way you create the set R, big R, was you take 0,1 to the VR and you sample R1, and then with the replacement IID, you sample R2, okay? So, and you sample that one. So you can think big R as a multiset, okay? So this means that Z1 through Zm are IID variables because these are, and there's nothing else random happening here, right? So moreover, the expectation of the random variable Zi is just the winning probability of the malicious prover against the full verifier, because each Ri, as we said, is random in the whole space, right? And their average of these random variables is exactly the winning probability against the residual verifier, because we're picking either R1 or R2 all the way up to Rm, one of them at random, in the residual verifier. Okay, so that is the winning probability against the residual verifier. You're just playing against one of these. All right. So by Chernoff bound, the probability that what we're analyzing can be rewritten exactly as the probability. Well, I'm opening the definition that this is the case, and by just replacing this one here with its expectation, as we did over here, right? And replacing this one here with, say, the expectation of Z1, for example, because they all have the same expectation as we did over here, right? Well, that is an expression of a Chernoff bound, right? What is the probability that the average of random variables that are IID differs from the expectation more than a certain amount? That is, some expression that is, this fraction squared. That's the square that often appears in the exponent of a Chernoff bound, and the number of samples. In this case, it's n. Okay. So this lemma basically that says that the prover with high probability over the choice of random set, capital R, the difference is large, is small, is just a direct application of a Chernoff bound to the right random variables. That's all. Okay? And the reason I'm doing it carefully is just because there's really I'm not hiding any steps. It's like a very direct, simple application. There's nothing deep going on here. It's just like the natural analysis you would do. Okay. Are we fine with the Chernoff bound application? Now, which Chernoff bound I'm applying? I guess. Okay, I didn't put it in the slides. Maybe I should state the Chernoff bound independently, but it's almost here, explicit here, but I'll still make it even more explicit. Basically, it is the Chernoff bound where if you think that this is delta, right, then you put here delta squared, and that's it, okay? All right, so we have established this claim. Notice we haven't yet used the fact that the transcript of communication is small, okay? All right, there's a question by me, why is this true? Well, remember that each Zi is a random variable that considers the verifier winning with Ri, but Ri is a random string in R, and is the ith random string in R, but each of the string is sampled from the full set, right? So that is what this is, right? One run of p tilde against the full verifier is the verifier where it receives one random string from the full set. But every member of the set capital R is such a thing, okay? So that's why you have this expectation. there is a question by Nishant. Do I mean 0, 1 to the VR or 0, 1 star? I can still write VR, just not count VR, right? 0, 1 star is maybe confusing because I'm putting no upper bound, and how do you count things and things like that. Just whatever is the verifier randomness, just bounded by VR, is just not a parameter that I'm including in the final result. It doesn't matter, okay? So I'm not relying on VR being anything. It's just whatever it is, okay? Certainly something is, right? Because the verifier runs in polynomial time, and I can just write this to be like whatever that running time is, right? So yes, VR is appearing here, but it doesn't matter for the final running time, okay? Of the algorithm. Good question. So further questions. There's a question about, can the verifier really not check? Yes, it really cannot. Because the verifier, the way it operates, it receives an explicit input and a choice of randomness. It doesn't know where this randomness comes from. This is a valid choice of randomness. It could have come from it's anything in 0, 1 to the VR. So the verifier just runs on it, and that's it. Great. So we have proved this claim. So now let's conclude. Now we're going to use the fact that the transcript is small. All right. How are we going to use it? The fact that p tilde, whatever arbitrary prover it is a function from the transcript so far to the next message, right? That's what p tilde is, right? It is a strategy to give me the next message. So because the transcript is small, there are not too many provers. There are at most 2 to the c to the 2 to the c provers, right? Because these are the number of functions from at most 2 to the c bits to at most 2 to the c bits. Sorry, from at most c bits to at most c bits, right? This is the number of such functions. So there's at most 2 to the c times 2 to the c provers. This means that if we drive down this probability small enough, we can take a union bound over all provers, okay? Because we don't have too many provers, okay? So the one place where we're using the transcript is small is that there cannot be too many malicious provers, all right? So by union bound on all such provers and taking m to be 2 to the c times c, right, which is this exponent over here, to be large enough, we have that the probability that there is some prover that makes the delta, this delta difference bigger than 1 over 10 is at most the sum that any one of them makes it large, right? So, but we know there's at most 2 to the c, 2 to the parentheses, c times 2 to the c, close parentheses, times whatever we already proved up here. So that's the probability, right? This is at most the number of provers. And because m is large enough and this exponent here is made to match this one with a minus in front and a large enough constant, we can just make sure that that one is, say, less than 1 over 100. Okay? So therefore, what we wanted to prove was the probability that over a random choice of R, the difference between the value of the residual tree and the value of the original tree is greater than 1 over 10. That's at most the probability that there is a prover that distinguishes the two sides, right? And is it less than 1 over 10? Indeed, for any choice of R, so there's a question. Oh, there's a question why there's at most this many provers, because any prover is a function from at most c bits to c bits. Okay, so p tilde is a function from, I don't know, 0, 1 up to the at most c to 0, 1 up to the at most c. Okay, so, and in general, the number of functions from that look like this is at most this. right? All right. Great. So coming back to how we conclude, so what we proved, so the fact that we can upper bound, we can use a union bound to make this probability small, like, relatively small. Now we're left to conclude that the probability that exists a prover that makes the difference large is an upper bound on what we cared about to begin with. And now we can see right now, like if there was, let's say that it was the case that the value of the residual prover for a particular choice of R is greater than the value of the original tree plus 1/10. That means that there is some prover, some optimal prover against the residual tree, and some potentially different prover against the original tree for which these probabilities behave like this, right? But whatever this prover is, okay, it can only do no worse, because it's the optimal one, than the prover that was optimal for the residual tree, okay? And so now, if I go from here to here, I see that is this P star R is the prover that makes the delta large, right? So whenever this happens, then this must happen because we had this, all right? And the other direction is symmetric. If you had the value of the original tree is greater than the residual tree plus 1/10, that means that there is some choice of optimal prover for the original game and some choice of optimal prover for the residual game that make this true. But again, there is going to be the optimal prover for the original game will not do better than the optimal prover than the residual game. And now in this other case, it is this P star that separates the delta, right? That makes the difference big. So this addresses the earlier question, what if you have different provers that achieve optimality in the different games? That's fine. By kind of what this argument here, okay? All right. Okay. Any questions about this? We've finished proving theorem 2. I've tried to kind of make in the slides everything absolutely explicit so that you can verify these things kind of offline. What was M again? M was the number of representative random strings for the verifier that we used to define the residual tree. Okay, so basically M is the number of random strings in R. All right. And we're picking M to be exponential in the transcript size so that we can absorb a union bound on the provers. Right? Because by making M to be large enough, then we can absorb this union bound on the provers. So I really, really like this proof because it is proving something non-trivial about the limitations in interactive proofs using absolutely quintessential computer science tools, okay? Union bound and Chernoff bound. These are sort of bread and butter of computer science, and this is basically the natural proof that would come out by analyzing the natural strategy, which is just subsampling the tree, okay? So this is like a very beautiful, straightforward proof with like no tricks, no clever steps. It's just kind of completely standard, okay? So definitely encourage you guys to look at it offline. And then for those of you that have some background in other areas of theoretical computer science, this should look like completely standard tools, okay? Union bound and Chernoff bounds are just sort of truly bread and butter, okay? So, and there's really nothing clever about this proof. We're just computing the value of a representative sample of the tree, this residual tree, right? And arguing that with this improbability, it is a good approximation of the original one. Further questions? All right, so before concluding, I would like to kind of shift back to this slide, because I would like to talk a little bit about what happens for the other theorems, okay? So we have proved in class today this one and that one, okay? And theorem 2, we proved it like, very explicitly, like we went through all the steps. So what's the deal with theorem 3, right? So the deal with theorem 3 is that suddenly we don't have a bound even on the verifier communication, okay? So it means that we cannot consider all the possible kind of next messages from the verifier, even if we subsample the verifier randomness, okay? So the idea is that we're going to subsample verifier messages as well, okay? And intuitively, we're going to do an analysis that is analogous to the one that we did, but separately for each layer of the tree. We're going to be basically saying, look, let's pick enough samples so that for every layer of the tree, it is representative with confidence, roughly 1 over number of layers. And then overall, like if the confidence of any given layer is like 1 over number of layers, when you add them all up, we have like a constant confidence over the whole tree, okay? So this is roughly called the hybrid argument, okay? And it's basically what is going to happen in the proof, which we're not presenting today, but if you're interested, I encourage you to look at, because it's a very good exercise. And it's actually like it is written out explicitly in that paper, okay? So essentially to prove theorem 3, it is just basically a more refined version of the strategy of theorem 2, except that you're applying it number of rounds times, okay? And because you're applying that strategy number of rounds times, you need to kind of set parameters so that you account for number of rounds as well. What if number of rounds is not constant? That's fine. You just, that's just whatever parameter it is, okay? So you make the confidence to be like 1 over the number of rounds. Since you have some number of rounds, 1 over number of rounds times number of rounds, that's a union bound that gives you something order of 1. Theorem 4 is quite different, or at least not quite different, but certainly like a step up. Basically, the subsampling that we were doing in theorem 2 and theorem 3 suddenly becomes quite complicated in the case of a private coin verifier, because it is difficult to understand how to make subsample random continuations, okay? Like it's not clear how to do it. And so the NP oracle is there precisely to solve this problem. It's essentially the proof of theorem 4 is the same as the proof of theorem 3, with this subsampling subroutine replaced by some other subroutine that uses the NP oracle with a help, okay? So yeah, so that's like roughly, and they're all in the same theorem that I mentioned by Oded Goldreich and Johan Hasted. It's very beautiful and accessible paper. Certainly encourage you to look at the proof of theorem 3. I think in the worksheet, there's going to be like a completely different approach to prove something, I think for IP, where you have perfect completeness. And maybe there was one other restriction. But anyway, some very nice proof where you assume perfect completeness, okay? But you do not assume public coin, okay? There's some connection to basically game theory. And in the worksheet, I think tomorrow, you're going to practice proving a pretty strong upper bound on private coin protocols with perfect completeness, okay? It's a very cute, elegant proof. But I think that's it, just the punchline for today. And this is like our last lecture in interactive proofs. Before we switch to interactive oracle proofs, is that not everything is possible with interactive proofs alone. It would be nice. And among the strongest limitations that we know in interactive proofs are precisely these types of theorems, okay? That the fewer resources you have in communication, the easier the language it can become to decide. And therefore that tells you that, hard languages, for example, exponentially hard languages, you don't expect to have like interesting interactive proofs for them, which is a pity, because examples like SAT, we want to have good probabilistic proofs for. Okay, and so for that, we're going to have to move to other models of probabilistic proof, such as PCPs or IOPs. Okay, so with that, I'm going to stop the recording and stick around for more questions.